Okay. Yeah. Okay. Well, good morning, everyone. Thank you for being here in this special meeting, which is devoted to the future instrumentation and future legacy projects for Calar Alto, for the Observatory of Calar Alto, and the director of the IAEA. The IAEA is an institution of the National Research Council, and this is a special privilege center in the sense that we are a very, very special and privileged relationship with the Observatory of Calar Alto. And then we are hosting here this meeting now, as we did in 2008, in June 2008, when it was a very, very special one and very important one for the future of the observatory those days, where the future instrumentation then was approved, was selected physically and scientifically, and several instruments were selected. In particular, was selected the Carmenes instrument and also the Panic instrument. It was very lively. I was there too. And then, so I want to recall that as a memory, but also as a milestone, because we want to do something similar in the sense that the future of the observatory now is in a very special situation. So we are looking for new challenges, scientific challenges, and this is just about the time to proceed and to help this meeting here. And I have with me the director of the observatory, which is Dr. Aceituno Jesus, and the organizer, the chair of the scientific organizing committee, Dr. Iglesias. So I will give you to give some words to the attendance.
Well, as you have told, I think it's obvious for everybody how important this workshop is for the future of the observatory. As probably most of you already know, a new scenario for 2019 is coming for the observatory, and we have to provide two answers for that moment. One is, of course, how the structure will be for the observatory. We are working on this, and probably you will get some news during this workshop. But this workshop is mainly, the main goal for this is just to answer the second issue, and is what the future will be, what we want to do with the observatory. On behalf of the observatory and myself, well, we are very proud to see how many programs, ideas, and legacy projects are going to be exposed during these 2 days. So that means that there is still a very strong interest on the international community for the future of the observatory. And this is a warranty for us. So in the name of the observatory, thank you very much to all the attenders and all the speakers for their contribution. Thank you very much as well to the Spanish Network of Infrastructure in Astronomy, who is supporting and financing this workshop. And well, I will tell more just in a few minutes. So this is everything I want to say.
Thank you.
Well, thank you. I would like just to add that we are more than 60 people from 8 countries and 3 continents registered to attend this meeting. And we will have even remote contributions from astronomers in China, United States, and France. And many other people worldwide will have the possibility to attend the workshop via live streaming. And we will also have contributions from technological companies, which are an essential component of the development of astronomical instrumentation. And we hope that we are able to find synergies among science and technology and to keep producing innovative results. And that's all. Thanks for coming, and we hope this workshop is fruitful for all of us.
Okay. Well, just a few words to end this opening. This is a formal opening, but it's, from the scientific point of view, most of us, we know each other. And the point was to close thanking, as you have said, acknowledging the support of the RIA, of the National Network for Infrastructure in Astronomy. And we were absolutely always supported by that, and also by his manager, Jordi Torra. He cannot be here at this moment, but he wants him to recover as soon as possible. Also this meeting was endorsed by our national association, la SEA, la Sociedad Española de Astronomía. His president sent his address to all of us. He's personally and the society that is, as a whole, is interested in the future of the observatory too. And on the other hand, we have strong support for institutions, and you will see that tomorrow from the national side. Francisco Herrada is coming from the Subdirección General of Infrastructure, just coming from the MINECO, the National Minister for Economy and Conocimiento, and also from the Junta de Andalucía, the Regional Minister from Economía and Conocimiento will be here tomorrow in the opening. Also the universities of Almería and Granada will be present tomorrow, and also the CSIC will be present with the Andalusian coordinator, the institutional representation of the Vice Presidency of CSIC. So this is just to get you a flavor of how important this meeting is seen. It's just a workshop. It's one and a half days, very packed, very compact, but we want that obtaining very, very important conclusions. And so thank you for coming, and I think we are formally opening the meeting, and we go for the first talk. Thank you.
So our first speaker of this first session is indeed Jesus Aceituno, who will talk about the near future perspectives for Calar.
Okay, thank you very much, Anna. Okay, so I'm just going to give some clues about what the future could be for the observatory, and some concepts that are very important also for us. I will start just with the main aim of this workshop. Pepe has already told something about this, but as some European report states, the 4-class-meter telescope have an important role to play in the front line astrophysical research in the beginning of the 21st century. So for that reason, we want to make an effort just to put Alto Observatory at the forefront of the astronomical research, as we are now, for example, with the success of Carmenes. For that reason, Alto, the IAA, and the RIA has organized this instrumentation workshop to gather outstanding ideas for the next generation instrument, especially for its flagship telescope, the 3.5-meter telescope, but also for the rest one, mainly the 2.2. But this is fully open to the rest of the facilities. I'm really happy just to see that there are even other ideas for the Schmidt camera, for example. All of them are, of course, pretty welcome. I think that here in Andalusia we have a very power instrument in astronomy. By one side, this institute is one of the more efficient institutions in physics in terms of publications at national level. And also in Andalusia we have the largest astronomical observatory in the mainland Europe. So we can talk now about a kind of Andalusian astronomy and astrophysical brand, and this may become a key element that may promote the technology development as a tractor of the economy. And this is a very important concept in the current times. For example, as a reminder, more than 50 companies have already explored the Carmenes development. This workshop also is a consequence of a previous work, as Pepe mentioned as well, that we celebrated a similar one in 2008, also in this home, that where many ideas also were presented, and one was selected, the Carmenes surveys and the Carmenes instrument, what is a really success, and it started working, as you know, in January the 1st in this year. During the day, or during today, there will be more talks that will update what the operation after 9 months working at the telescope. And this talk will be given by Pedro and Andreas Kirchenbach. These are some pictures when the instrument arrived to the observatory during the previous year. But I don't want to stop here much because, as I told, there will be some specific talks to explain this. This workshop is not open only to instrumental ideas, but also for legacy projects. And this is a distinguishing mark of Calar Alto, because Calar Alto is one of the few observatories in the world that may provide large observing slots for legacy projects. And this is something that we are doing since 2010 successfully. Specifically, there are two of these legacy projects that we are in past a very strong highlight. For example, the Alhambra survey, around 16 institutions we are working on that, and more than 70 scientists we are involved. We allocated around 360 nights for that legacy project. And Khalifa one, for example, with this legacy project that has finished the last year, there are around 118 papers with the string Khalifa in the title, around 160 papers with the string Khalifa in the abstract. There are more than 270 citations, and more than 45,000 data queues already downloaded. There are, if we consider the thesis in preparation and all those ones already defended, there are around 30 theses for this legacy project. What I think they are amazing numbers for the legacy project. As you probably know, 2014 was a very difficult year for the observatory, where the crisis hit us very strong. But fortunately, we found the way just to go out. I just want to mention here some of the main scientific highlights that we got during 2015, just to give you an idea of what's the current situation of the observatory. So one of the highlights is we have a new visitor instrument, the Planet Cam. It's fully operational at the Alto Observatory. This is a Basque Country University development, and it's in operation at the 2.2. We may offer this for external collaborations. And this camera is a twin lucky imager that works simultaneously in the visible and in the infrared. So we have closed during 2015 several collaborations with external partners. I mentioned here only some of them. Like, for example, with the University of Nanjing, another visitor instrument coming from the Observatory of Paris, so-called Miosotis. Collaborations, a very important one with the European Space Agency for the exploitation of the Schmidt camera, which were working until March in 2017. This is strategically very important for us. Other collaborations with the Denmark Technical University, with Spanish University, with the Technological Institute of Tokyo, there are a lot. These are only some examples that show you what the interest of the international community is for the exploitation of the observatory. Not during 2015, but early in 2016, the third data release of Khalifa has been published. As you know, this is the first IFS study designed explicitly as a legacy project, and it constitutes today the biggest study of this kind ever finished. So with this workshop, we want just to follow those steps. There are also two instruments working. One is Carmenes, that I told, that started working in January the 1st of this year, but also PANIC, the panoramic infrared camera, that since 2015 is offered as a standard instrument, and is consuming around 15% of the total observation time at the 2.2. With all the data collected by the Calar telescopes, there are, in 2015, a total of 110 papers, referred papers, what is not that bad comparing with other sites. In terms of effective, if we compare the budget with the number of papers, this is a really beautiful number, if we compare with other observatories, for example. We are also making some efforts in the tourism issue, where around 500 people are visiting Calar Alto monthly. But please don't be wrong. I mean, we are not losing our main aim. We have a very clear idea that the main aim of the observatory is the astronomical research. But we understand that we have to provide an answer to the population, because they have a very strong interest just to know what the observatory is. And for that reason, an external company, so-called Azimut, is fully in charge of this issue. This is our current panel of instrumentation. So for the 3.5, 80% of the total observing time is devoted for the Carmenes survey, and 20% is offering open time. This is because of the Calar Alto is an ICTS. This concept I will explain later, because it's quite important for us, and it's one of the clues how to find some funds in terms of new developments. During this 20% of open time, the instruments offered are Carmenes, Pimas, Leica, and Omega 2000. In the case of the 2.2, the instruments that we are offering are Panic, Café, CAFOS, Busca, and PlanetCamp. I guess that most of you already know the details of those instruments, but if not, and you are interested, please visit our webpage. Something new for this telescope is that we have partially opened the time to external worldwide customers via selling time. Any customer, independent if they are in the standard partners or not, may get some observing time by purchasing time. That's the case of some of the collaborations that I told you before, like the DTU, the Observatory of Paris, the Nanjing University, or the Tokyo Institute of Technology, between others. And of course, because the 2.2 is also an ICTS, we have to offer a 20% of the total time as open time. In the case of the 1.2 telescope, we are offering at the moment CCD, but we are exploring the possibility just to attach as well a long slit spectra. And this is offered fully in open time to external worldwide customers via selling time. If you want to make a legacy project that consumes a lot of time, the 1.2 is also suitable for you. And finally, the Schmidt telescope that, as I told, is now fully dedicated to one program, and now the European Space Agency is taking care of this. This is quite important because they are supporting all the costs of working. As I told this concept, ICTS is something very important for us. ICTS means singular scientific and technical infrastructure. These are big facilities with resources and equipment that are unique of its kind. They are based on the state-of-the-art of the technical development that promote the knowledge and the transfer of the technology. There are a total of 39 ICTS in Spain and several are devoted to astronomy. Alto is one of them. Maybe the easiest way just to understand how important for the main government an ICTS is as the Mineco states. Let me read because I think that is pretty clear. ICTS is a singular scientific infrastructure, an experimental vanguard tool unique in Spain due to its contents and performance, useful for the research, development, and innovation system of our country, scientifically and technologically developed, essential in order to achieve a specific research and or technology development, so that its non-existence represents a limitation or loss of opportunities for the country, and whose construction and or conservation is mandatory and strategic. I think it's pretty clear what this means for the main government. Something good just to be an ICTS is that there are special funding lines to make new developments. For example, the so-called program FEDER 2014 and 2020. This is supported by the Spanish Ministry of Economy, and the main aim is to enhance scientific research and technological development and innovation. This is suitable only for ICTS. And the actions supported are new developments, updates or improvement of existing facilities, and repairs or substitution of elements of the map of infrastructure. That means that any instrumental idea that comes from this workshop or any other could be found by these financial lines. This call is continuously open until 2020. They are evaluated quarterly. The requirements is that we have to present a letter of intent, a report with the technological and economical issues, and the actions, this is something important, must be included in the strategic plan of the ICTS. Okay, in our approved strategic plan, it is foreseen the development of a new instrument for the 3.5 and 2.2 telescope up to 5 million euros. So this is a clue what we could do, whatever happens with this workshop. The total contribution for this program is around 180 million euros, and in Andalusia there are 6 ICTS. Something good that Alto is in Andalusia is that we can benefit of a total of 80% of European regional funds. So we have to worry only just to find the remaining 20%. But in any case, I think that this is a very nice opportunity. We have already applied for this program, and it's not the only line just to get funds. So during 2016, we have already been granted with 2 actions. The action grant was applied to this program that I mentioned, and we got 1,130,000 euros. We want to do with this an energetic island just to optimize our resources in terms of heating and electricity, and also to make a full upgrade of our spectrum of cafe. In the action 2, that is another line different to the program FEDER, is the so-called improvement of infrastructure. We got close to €1 million already, and with this we want just to update the panic instrument. We have got funds just to substitute 2 of the detectors, to update completely our visualization system, and some spares for cameras. So I encourage you, just even for all the instrumental ideas, just to follow those steps. Okay, during this workshop, we will also give some clues about what the future will be. I think that is the main idea in our brains at the moment. Maybe I should start with some of our history, main dates. As you may know, Alto is an economic interest group formed by the Max Planck Society and the Consejo Superior de Investigaciones Científicas. By the Max Planck, our reference institute is the institute located at Heidelberg, and by the CSIC is this home. So, well, everything started in '68, where different site testing were made in different places, mainly in Spain and Greece. In '72, the first agreement was achieved between the governments of Spain and the Federal Republic of Germany. In '75, the first facility was built, the 1.2. In '79, the first light for the 2.2 happened, and also the Schmidt camera was transferred from Hamburg to Calar Alto. Also, the 1.5 Spanish telescope was built. That was the official inauguration of the Centro Astronómico Hispano-Alemán. Finally, in '84, the 3.5 was finished. This agreement finished in 2003, and a new one started in 2004 with the joint operation 50-50 by the Max Planck Society and Consejo Superior de Investigaciones Científicas. As a special date, I put it here in Carmen's because I think it's one of the most important highlights in the Calar Alto history. Okay, and about the future, well, as you know, the current agreement of Calar Alto will end in December 2018. This is because the Max Planck Society will leave the partnership. So now it's very urgent just to find a new partner or partners to substitute the German partnership and just to join to Consejo in this adventure for the incoming years. We are just working with this, and we have already celebrated some meeting with Junta Andalucía, who seems to be the most feasible partner at the moment, and indeed they have already shown a very strong interest in this matter. For example, in this link on the webpage of Junta Andalucía, you can see when the president of this government came to Calar Alto for a visit, she commits the support of the Andalusian government for the continuity of the observatory. Most probably tomorrow during the authorities table, you will get more news. Not only the Andalusian government, but also the main government. I mean, they also have already visited Calar Alto, and in different press releases, they have highlighted the effort just to guarantee the viability of the observatory of Calar Alto. Okay, why to do all these kind of legacy projects and these kind of new developments for Calar Alto? Well, I think that we could maybe make it, I don't know, hours and hours just talking why to do that. But I think that it's important just to highlight this, that Calar Alto is the largest observatory in the mainland Europe, and this is something good in terms of for optimizing resources in case that you want to make a new facility or a new instrument development or something like that. Is, as I told, one of the few observatories that may provide a large slot of observing time beyond 2019. There are not many observatories that may do that, and this is extremely important for the legacy projects. We have a very wide expertise, a very well-trained staff, a long-standing tradition developing outstanding instrumentation in collaboration with many institutions, and we have shown, for example, with Carmenes. It's an ICTS, so we have a special funding line for that. As I told, 80% of the European regional funds can be used for these new developments. And of course, we have a very excellent sky quality. So I will say that we have all the components just to make real any of the legacy projects or the instrumental developments that will be shown during the next incoming 2 days. So that's basically all. Thank you very much for your attention.
Questions?
I found quite interesting your remark on the importance of technology transfer. From my own experience, I find this very difficult to accomplish, so I would be curious to learn what ideas you have in mind and what, from the outside world, the expectations would be to Colorado Observatory with regards to it.
Well, at the moment we are just working very hard as well with the universities because I think that they are just the right tool just to make this transfer of technology. At the moment we are just closing new agreements especially with the University of Almería and also with the University of Seville, that they have a very long expertise in this sense. We are more or less new and we don't know how to do all these kind of things, but we have the help of those universities just to, I think that is quite important. I mean, just when a new development, like for example, like Carmenes, it's quite important just to properly do this transfer of technology. And just to do that, we will get the help from the universities.
One more question? All right, if not, thank you again, Jesus. We continue with Martin Roth, who will talk about innovation for astronomical instrumentation.
So, we're taking it down. Thank you very much, Anna, and thank you very much to the local organizing committee and the SOC, Jesus in particular, Jorge, for organizing this very important event. And I do remember of having participated in the Calar instrumentation workshop that was mentioned several times already in 2008. So I'm really positive that the impact of this event today will secure the future after 2018. And it was quite interesting to hear what the perspectives are. I'm really looking forward. I feel honored to have an opportunity to make a contribution today. And I think you will be not surprised that my contribution will be very focused. So please forgive me for my bias, but no kidding. This is my license plate.
No, really?
Yes, it is. PM stands for Potsdam Mittelmark. This is the county where I'm living. Anyway, this is a little bit of the funny side. But there's an interesting point in this. This is the year of when we started the PMAS development with the first grant from the RIA in Germany. As was already introduced by Jesus, we have some statistics of the impact of Colorado, instrumentation and particular legacy surveys. Santos is here. Thank you for yesterday providing me with the actual numbers of papers that are actually based on PMAS data. Over the years from, you probably can read this very well, 2003 to today, where we have a total of almost 200, which I think is not too bad for an instrument that was planned with a team instrument. In our inventory in Potsdam, it's still the Reise spectrograph travel instrument. Well, here's to support this, the citations to the reference paper of the instrument. There's something to say. The title of my talk has to do with innovation. I will skip this because Christus has already forwarded information on the impact of the Khalifa survey. If you're interested, come to me later, because Sebastian Sanchez has distributed this two days ago, the PI of the Khalifa survey. But I want in this talk to concentrate on innovation and what that means and how this has played a role in making PIMAS at Calar Alto a success. So in this presentation, I want to first venture a definition of the term innovation, and then spend some time on a case study, how innovation can work. And I want to give an additional facet to what you have proposed, to a future role of Calar Alto in terms of enabling innovation. And then I have very shortly 3 proposals that are not really proposed, they're ideas, and I have to contribute to the brainstorming that I expect from this workshop. Okay, so about the term innovation, if you look into the literature, there are multitudes of definitions. I found a paper that has summarized the research and found 40 definitions. The one that I will adopt is that you make a distinction between an invention and making an invention a success on any kind of market. And an astronomy market would mean astronomers utilizing a technology, right, and writing papers. What people doing research on innovation have already in the year of 1903 proposed, well, this is not really well defined except for the time, growth of any entity in the area of innovation, where you have a current technology that is settled, and then you have an emergent technology, which for some reason is very successful, and then is really yielding impact on any market until you reach some saturation. And the point I wanted to make with regards to PIMAS is that risk apparently plays a great role. And what I found is that the Spanish community was extremely active and curious to what was in the 90s an emerging technology utilized for their research, intermediate spectroscopy. And I think for the case of PIMAS, we can claim that this steep curve was really supported by the community. And I think this is something one should keep in mind, risk and the ability of researchers to take on risks for the benefit of their research. In Potsdam, we are operating an innovation center with substantial funding from the Federal Ministry for Science and Education. It's located in this building. It has an unspeakable acronym, InnoFSpec. It stands for Innovative Fiber-Based Spectroscopy and Sensing, where we hope to support such a process of enabling technologies to yield a progress in fields that are, and I'm pointing to a talk in terms of one particular subject, astrophotonics, to be given by Stefano Minardi, who is a team leader that has just started in September for a 5 years time of operation. But in general, where we intend to provide research in this field of spectroscopy that is based on fiber coupling for various fields, not only in astronomy. And I will not go into this magic graph very much, but just say that, sorry for this, it's taken from a strategy document in German. We are starting with topics, work out methodologies, develop components with the final goal to make systems to work. Yeah? And there are several examples that we have here, and they cover physical chemistry, which is the partner in this center at the University of Potsdam, and astronomy. If you want to pick out a few, you could say spectroscopic surveys, but also studying scattering properties of solutions and dispersions and so forth, cavity ring-down spectroscopy, or integral field spectroscopy for methods and so forth. So the idea is to really cover all those areas with the hope that others can use and utilize the systems that may be emerging from new technologies. And we have some examples here. The most recent one being Mosaic in know what we're talking about, and maybe we can create some synergies with Calar Alto, and this is what I'm going to propose later. Okay, having said this, I just want to mention that as of the 1st of October, we have yet another research in our center that does play a role for one of the proposals I'm going to make. I also want to mention, and Jesus has highlighted this as a goal as well, that networking plays a great role. I'm in the executive board of a network called 3D Sensation, which receives 45 million euros of funding over 5 years, where a lot of companies are involved, but also academic institutions. And I find this extremely useful, but I warn you, it costs a lot of efforts to support the networking indeed. Okay, now the second part of my talk is dedicated to highlight this curve in an example that I know very well because it has been a dream since 1996. Remember my license plate. And it concerns resolved stellar populations, where I was when I learned about infrared spectroscopy when I moved to Potsdam in 1993 from our Russian police, by the way, that there was a way to transfer what we are using for ages. It's a standard tool, PSF fitting photometry, since the advent of CCDs, to transfer this to data cubes. And it has taken a long time to really go up on the innovation curve, and I just want to show you a few highlights and illustrate what the role of Calar Alto has been. So my first commissioning data experience on Calar Alto has, after some time, resulted in a paper where we investigated only a handful of planetary nebulae in the bulge of M31. This is very difficult to do because surface brightness is limiting the ability to do spectrophotometry, where you see here the spectrum. I can't go into any of the detail, but just scratch the surface to give you an idea. This was the first time we have experimented with PSF fitting technique to dig out the point sources from the very bright background. In a broadband image, there's no way that you can see a planetary there. The real breakthrough, I think, came through the thesis of Sebastian Kamann. Some of you in the audience know Sebastian, he's now in Göttingen. Where he systematically developed, based on simulations, numerical simulations, a code that comes by the acronym of Pampelmuse. Don't ask me what exactly this stands for, but Muse is the instrument that it was targeting in the end, where Sebastian and I went observing with PMAS on Calar Alto to study globular clusters. And the idea is illustrated here. Here you see an image of the nuclear region of a cluster M3 obtained with the Hubble Space Telescope, and this is the reconstructed white light image from a Muse data cube. If you look carefully, you can perhaps compare these three stars, or the suite of stars here. Seems to correspond given the ground-based image quality that you can obtain, which was not so bad at this time. So if you do the PSF fitting, then you can compare with the residual. And by the way, the red circle is the nucleus of the cluster. So for one star, apparently for the reconstructed light, this seems to work, but the spectra, this is a spectrum of the single star, and the calcium triplet region shows you that indeed you are able to extract a spectrum that looks okay. And the bottom line is, if you do this with the help of the HST data, where you have a priori knowledge where you expect the stars, then you can expect to extract the whole lot, and this is shown here. This was published in 2013, a few years ago, but it was done for several clusters, and well, you see a mosaic because the field of view of PMAS is so small, with the sampling chosen here, it's 8 arc seconds. But one of the important results that was so far impossible to be obtained is when you see the velocity dispersion obtained from the many spectra that were measured, plotted versus the logarithm of radius, where you see published data in the literature covering only the outer parts of the cluster. We have now 2 more points, and the curves here show different Lean models of the hypothesis of a central intermediate mass black hole, where the mass is labeled here, and the new data shows that you could live with actually the absence of an intermediate mass black hole, which is a very controversial subject in the literature. So I think this was a nice example obtained for the first time at Calar Alto. And again, I would say this is a high-risk project. You will not get time at ESO, for example, or at Keck, I would think, with such a project. Now, but given this first result, we could move on and actually propose for our Muse commissioning time. This is another cluster, NGC 6397, one of the closest cluster to us, 2.4 kiloparsecs or so, very metal poor. Now, this is a mosaic of Muse pointings. For comparison, this would be the field of view obtained by PMAS, and we really cover a large fraction of this cluster with snapshots of 1 minute per field. There are 2 papers resulting from this already. This was just, as I said, commissioning data, a quick shot exercise. And the result is that from this lot of data, we have 12,000 spectra. 12,000 for all these stars. And if you focus on this field, just a technical aspect of it, here is this tile, and then zoom in into the red square, what you find is for the reconstructed Muse map, as I've shown you for PMAS, the other example, and the comparison HST field, a one-to-one correspondence of stars. But if you focus on what is seen here as a blend, in HST you see from the diffraction pattern that this must be very mostly spaced 2 stars, that indeed the technique has been able, for the red cross and the green cross, to yield 2 different spectra. One of which is a G star, where you see nicely the calcium triplet, and an A star with broad Balmer lines in the Paschen series. Very nicely deblended. So I was very proud when I saw this result, because it has shown that what we have exercised on Calar Alto is now being taken over on larger telescopes. And I can tell you this is now a large effort in GTO time of the Muse science team, providing very, very exciting results. Just again from the technical point of view, here is CMD based on HST photometry, but the color coding shows you the signal to noise obtained. So at the turnoff, you're in the area of between 20 and 50, and here on the RGB, you are beyond 100 signal to noise ratio. It's very nice. And even on the main sequence, you can do some then less reliable work. And from that, for example, you can make an HRD. I will skip over this and come to the next step of now possible innovation. This is still work in progress. And I must say, I could not resist to grab my old slides of a conference, Metals in 3D, held here in Granada. They organized this wonderful workshop in 2012, where with help of Carolina, for example, who was on the author list, we proposed to carry on this idea of crowded field spectroscopy, not only to nearby globular clusters, but also to galaxies. Well, this is from the slides, you know. And I pointed out the advantages that this technique would have. With a Muse data cube, we would have the equivalent of 4,000 extremely narrowband filters. So this would be providing unprecedented sensitivity for narrowband imaging, if you like, i.e. emission line objects. But it would also allow for point split function fitting spectrophotometry of stars. That was the idea. And of course, one of the nearby objects that come to mind on the southern hemisphere would be the Sculptor Group galaxy NGC 300 with a distance of a little bit less than 2 megaparsec. So I remind you, this is a factor of 1,000 further away than the globular cluster that I've shown you in the previous slides. So this is really challenging. Now, let's focus on this field, and we have obtained so far 7 pointings with Muse of a duration of exposure time 1.5 hours. This is the nucleus of the galaxy, and here you have labels for the seeing. So we have excellent seeing here, and not so good seeing in those pointings. And if we do the exercise again and make a reconstructed map, now in the colors, VRI, the result from Muse looks like this. The background is a wide field imager picture, and here you have you can nicely see how the spiral arm extends here. And now we can see whether we can do the exercise of PSF fitting technique again. And I want to illustrate how this works. In the case of the best seeing field, dubbed A, so you host of blue stars, red stars, also dust, etc. Now, I probably don't have time to go into the details how to do this. I just mentioned a few keywords. Backing up this with HST photometry, we use the Pampelmuse tool. And then we go ahead, because you yield typically per field 1,500 useful spectra, some tool, and I've used ULIS with a spectral library, which is basically the Mielens library, plus the calcium triplet region, plus what Alexander Watzdickes has worked out to bridge the gap from the Indo-US library. And then we have, as a control, used what I have not introduced so far, the Göttingen library of model spectra based on Phoenix models. And in the end, then, from the proposed spectral types, make a visual inspection and see how reasonable that is. Oh, by the way, also yield radial velocities. And how well that works, I want to show you now. Remember, this is heritage from Calar Alto, and extremely excited that this works. Here you have blue spectrum. If you look on the panels here, I hope you can see this sufficient contrast. This is the HST image. Here is the blue star. And this is the reconstructed color map from the Muse data cube, a little part of the cube that focuses on the star. Then we have the proposed solutions from the ULIS code. And here I isolate what I think is the most probable solution. So this is a B subgiant at a magnitude of 22.3, and a radial velocity as given here. Signal to noise is 7. Here you see H beta, H alpha. So we say, okay, so this is a bit at the edge. For blue stars, I would agree. Another Starlin giant of spectral type A, HST, ground-based. Here's the magnitude. But here you have a case where the signal to noise is very high and the magnitude is 20.6. If you look into the HST image, we have an indication that there's a blend with a resolution, or say a sampling rather, of what is 2 parsecs at the distance of the galaxy per spexel. You cannot resolve OB associations. So I guess this is probably a blend, as is suggested also here, but with prominent contributions from A-type supergiants and subgiants. If you go to cooler stars, this is a K star, calcium triplet, magnesium 1, the sodium doublet, and even cooler stars. This is a very prominent example that really springs out clearly an N star, given the titanium oxide bands, get rid of effective temperature and gravity suggestions, but also radial velocity here. You have hints of the calcium triplet again. And then, quite similar to this spectra, if you compare the two, one case that I'm, again, very proud of, because if you look into the map, in HST you see the N star here and another blue star close by, but they're well separated. But from the ground-based observations, you see this is fudge that is merged. So you have been able to take out this red star with apparently no crosstalk from the blue star, which shows that even at the large distance that we have for those stars, remember 1.8 megaparsec, we're able to deblend this. And if you move this a little bit, you see, focus on the blue star, and it comes out, and it turns out to be a late B type or early A supergiant. So I think it works. Now here's an example where the fit collapsed. It's very hard to see in the audience, I admit. The red curve would be the fit, and I'm not impressed. I thought this is spurious or whatever. But I thought, well, the star is so well visible. Let's do a little bit of research in the literature what this spectrum could be. Now if you compare, this is a carbon star. So now as I have investigated this one field called I, the one with the best seeing, I have already found 14 carbon stars, which is interesting because I've come across a paper published only in September that summarizes 10 years of splash work on Keck with using DMOS and imaging work from other observatories. They found in the halo of M31 and satellite galaxies to M31, again from 12,000 stars total, 41 carbon stars. So you see, this is very efficient. Okay, I probably don't have time to discuss how many planetary nebulae we find, H2 regions, compact H2 regions, supernova stars. also interesting emission line stars. Come and talk to me with a coffee break. But I want to finish this section with showing you again the map, however, of velocities. This is again very preliminary. This is scale here. And I remind you this is the nucleus. So round about the nucleus, where I remind you the systemic velocity of the galaxy is 144 kilometers per second. This is round about a scatter of this systemic. And then you see increasing radial velocities the further you go out in the spiral arm. And it rotates like this, so it's all in line. So I think we have already now a handle on the basis of individual stars to measure kinematics, which is very interesting in terms of studying migration along spiral arms, etc., that is being proposed from numerical modeling and so forth. So the third step, which is future of what we are proposing as member of the Mosaic Consortium towards building what is called ELTMOS on the European Extremely Large Telescope, would mean that, where I'm referring to you to a recent SPIE paper of the PI, to, well, use the capability of the proposed instrument consisting of single pointing IFUs, single fibers, so to speak, of order 200, and deployable mini IFUs of the size perhaps of the PMAS lens array of number 10, so to speak, to actually carry this to the next level. At a 40-meter telescope, you would obtain the same kind of spectra that I've shown you, not in 1.5 hours, but rather in 10 minutes. And I have no time to discuss the various science cases, but I would say that for those that are listed here, resolved stars and nearby galaxies, the technique that we have developed in Calar Alto would really be a very interesting application. And just to visualize this is Calar Alto, M3. You have seen these images. This is what we just are achieving. It's not yet published, but soon will be, obtained with MUSE on the VLT. And this will be the future Mosaic plus, by the way, the Mikado imager. So that's the kind of vision that I have. And I think Calar Alto has a fantastic opportunity to not having the same pressure as a 10-meter telescope to engage in risks. And we have been endowed with time to do other experiments. And this is my contribution, I think, to the brainstorming of future applications when we are talking about innovation. Yeah, and this is my answer. Okay. Now I will give you a little sketch of ideas that crossed my mind. I've had no time to tell you about our activities at the Aspect Center in Potsdam, where we have reached into other regions by applying astronomical instrumentation to medicine. But the benefit we have from these activities is that we have currently 3 spectrographs of the MUSE type in our laboratory that I'm offering to potentially, starting from today, in a sequence, because some of the instruments are still being used for experiments with the Charité Clinic in Potsdam. And if you'd like to learn more details, talk to Benito Borjalejos. Benito, are you here? Benito is doing this kind of research. But when these experiments will be finished, we of course have in mind to utilize those spectrographs for astronomy. So what I could imagine is along the lines of the setup of the MUSE instrument, which is a battery of 24 spectrographs as modules, to perhaps put this on the floor of the 3.5 meter telescope. Something that would be scalable, fiber coupled, as opposed to MUSE, which has free space optics coupling with slicers, which would allow you to either have, for example, mini IFUs, much along the lines of what I showed you for Mosaic. You could also envisage single fibers, like now being built for Weave or for Foremost and other observatories. Or you could envisage to have a large, let's say, super PPAC as another alternative, with the limitations of the resolving power that is provided by those spectrographs. This is technology push in the speak of innovation management. Technology pull would mean that the astronomical community desires to have such instruments. So this is, I think, a good marketplace to exchange views. I must tell you that AIP does not have resources to really develop a concept and an instrument, so it would be necessary to find a PI institute that would be interested to do something like this. My second, well, this is the spectrograph, and there will be, as I already indicated, an extra talk by Benito later tomorrow, I think, where you can learn about the details today, details of this technology. It's a clone of the Muse concept. And we have worked this out already many years ago as a proposal for an upgrade of the Flames facility. It did not go through, but I think the arguments are still valid. If you are interested in more details, I can provide you with the text of that proposal. So the second point that will be just very quick has to do with a major limitation that we're encountering when we are talking about extremely large telescopes and their operation predominantly in the near infrared, which is the infrared sky emission. You're all aware of the OH, which is very strong and a real problem for low to intermediate resolution spectroscopy. Now, since quite some time, with partners in Australia who have developed a scheme of OH suppression, we are working at InnoAspect to build fibers that have notches to block out on the order of 100 such emission lines. And a prototype has been built in collaboration with the University of Sydney and the AEO between Potsdam and our center that is now being planned to be tested on the Praxis instrument, another SBIE paper from the Edinburgh conference that you can look up the details of. Anyway, just the idea is that you have here for this demonstrator experiment a spectrograph. You have an IFU. And here you have the filter, and everything is coupled with those fibers. And the filter is based on special so-called fiber Bragg ratings. It's a very, very complicated technology to make many notches of the specification, but I can show you the performance, how it works. So here in the H band, you have for the current filter technology 100 notches of different depth, typically 25 dBs. And a zoom in on one such notch shows you that you have an almost perfect rectangular shape of width roughly an angstrom. So you're blocking out the line, and you make sure that no scattering light is generated within the spectrograph that would appear as, rising artificially the continuum background. That's the idea. A first experiment has been conducted at the AAT already with a not very sufficient instrument called Gnosis, which is why we are now engaging in Praxis. Now, I told you that we have a second group at InnoAspect starting now. And we will continue our efforts to build those specific filters. And I imagine that we could foresee a pilot study experiment at Calar Alto if this was of interest to the community and further develop this, perhaps with some synergy of Carmenes, because there we have a high resolution instrument that could help us to identify how exactly the quality of those notches works. And this could save one problem that we have found with mosaic. It has just been discovered only recently that for certain settings, already within 80 seconds, the exposure would be saturated because the light collecting power of the ELT is so large. And this will concern other instruments as well. So they have many problems, cannot accept to have the saturation happening, but so you have to break down in smaller fractions, and you lose a factor of 3 typically to the nominal exposure time of your estimate to get a given signal to noise because of the additional noise sources. So this could be actually, in the sense that I was telling you on the innovation curve, a good contribution from Calar Alto as well. And the final one I will not explain in detail because I'm running out of time. We have already tested laser frequency comms of a novel type with PMAS. This was very encouraging, and I point you again to Stefano Minardi's talk, who will talk about astrophotonics and general aspects. So this is another area where I think we could offer to make contributions to the innovation aspect that was mentioned by Thyssus. And I think this is the end. Thank you.
in the proposal one, how would it be the new front end? Will be less massive because you will put optics set on the ground, right?
Yes. The first consideration that we had was the worry that PMAS, which is in pretty good shape, mechanically speaking, electrically speaking, however, has technology that is 20 years old. So we are always a bit anxious that how long it will survive. We have spare parts, but I think we cannot subtend the operation, say, beyond 10 more years or so. So we have to think of the future. Now, because we initially, as I told you, were planning PMAS to be a traveling instrument, made the design such that it was self-contained and could be plugged onto the LBT, for example, or the VLT. It did not happen because the demand on Calar Alto was so large that there was no compelling point to bother in the first place. But I think the design as it is not ideal for 3.5. So as you point out, I would think that one would have to reduce the weight, put down all of the elements. I was brushing a bit quickly through that particular slide, but we would have, if in the ideal case, 3 spectrographs of the Muse type plus the one from PMAS that we could combine. And then the front end, you would have to decide what you want to go for, whether it's a large monolithic IFU, a super PPAC, but it depends on the science cases, if this is warranted or not. I'm not so sure whether this is really true. But deployable IFUs then would incur that you have a positioner where you could decide to make a very complicated development of an automatic positioner, or perhaps something that Sloan is applying plug plates, which is perhaps more practical and quick. So a lot of detail to be thought of. But yes, I think the load on the cathode grain would reduce dramatically. Plus the heat sources, by the way. And I want to point out something else. I encounter many occasions where even the 0.5 arc-second sampling of the lens array is undersampling the image. So I think Calar Alto has not the greatest reputation of seeing, but it's entirely wrong. You can have periods of fantastic seeing, and I'm not sure whether PMAS is exploiting this at this point. One could think about perhaps a clever scheme if you were able to schedule very, very flexibly on the order of minutes to utilize periods when the seeing is fantastic to do things that you cannot do elsewhere. And I've not expanded on this, but the images that I've shown you for NGC 300, I mean, the depth you can obtain very critically depends on the full width half max. And there's a large difference between 0.8 arcsec and the 0.6. So this would be another idea.
More questions? All right, if not, thank you very much, Martin, again. And we go to the podium, Laurent Dirissen, who will present CITEL.
Yes, I would like to thank the organizer, and in particular Jorge, for inviting me to talk about the project that actually I spent most of my days and nights for the past 10 years or so. And I'm very glad actually that Anna is the chair for this session, because Anna and I met for the first time maybe 23, 22 years ago. She was a student in Baltimore, and I was a postdoc in Baltimore with my wife, and so we haven't met in 21 years or so. So the instrument CITEL is the instrument we have, our team has built for the Canada-France-Hawaii telescope. And the CFHT is very similar actually in many points to the Calar Alto 3.5 meter. It's a 3.6 meter. It has been built in the early 1980s, so more or less the same kind of telescope, and the need also to bring new instruments to make sure that the telescope is still worthwhile. So the first part of my talk will be rather technical to explain what CITEL is, and the second part will be more scientific about the results that we have obtained so far in commissioning and science verification phases. So what you see here is a part of the data cube that we have obtained of this, the center of this cluster with NGC 1275 in the core. So this is more or less the whole field of view, not quite, but maybe 75% of the whole field of view of CITEL, which is 11 by 11 arc minutes. And this is part of the data cube only for this part here, but I will come back to this in a minute. So essentially, what is CITEL? It's an imaging Fourier transform spectrometer, a large, very large IFU, with a field of view, as I mentioned, of 11 by 11 arc minutes. The spectral resolution, you can decide just a minute or two before you do the observation, so it's very flexible in this sense. The instrument is capable to go up to 20,000 and even more, but we have only tried it and pushed it to a resolution of 5,000 without any problem so far. It works in the visible band, and I did all I could to push the instrument in terms of detectors, in terms of efficiency, as far to the blue as possible, so it's still very efficient at 350 nanometers. I was motivated by the oxygen 2 line at 3727 angstrom, and it goes to the near infrared as well. And the detectors are 2K by 2K CCDs, and we have two of them, and I will explain why in a minute. So it provides 4.2 million spectra, and that's just too much. The team, we are a very small team at Université Laval in Quebec City. We worked with ABB BOMEM, which is a Quebec-based company. Well, BOMEM is a Quebec-based company. ABB, of course, is the big company that owns, I don't know how many plants around the world. But what I liked about working with them is that all of these people are former students. The main engineer, Julie Mandard, was my master's degree student. Frédéric Gramont was my first PhD student a long time ago, and all of them were former students, so it was really fun to work with them, even if they work in the industry now. People at CFHT also, they worked on essentially the CCDs, and people at Université de Montréal also worked on some part of the project. But it's a very small team compared to, for example, the Muse team, which is huge and enormous. And I met Roland Bacon in Toronto a few weeks ago, and it's just incredible the difference between the size of the two teams. But still, it's so fun to work with a small team. So essentially what CITEL is like a normal camera. There's a collimator, camera, CCDs, but at the core of the instrument is a Michelson interferometer. So the big technical challenge that we had to overcome was about the stability of the Michelson interferometer. Because you have probably seen and worked with Michelsons in the lab, and you know how sensitive these are. But in the lab, it's okay to work with a Michelson. But you can imagine putting a Michelson on a Cassegrain focus of the telescope with the wind and everything moving around, and it's very difficult, especially if you want to go down to 350 nanometers. So this is the official picture of CITEL. So the collimator around here, Michelson here, the two cameras right here, and the electronics outside. So as I mentioned, the CFHT is very similar to the Calar Alto 3.5 meter telescope in terms of structure. The size also of the primary mirror, so CITEL is right here. CITEL is not the first FTS to work in astronomy. There have been examples before. At the CFHT itself, an instrument called BEAR, which was an imaging FTS working in the infrared part of the spectrum with a small field of view of 24 by 24 arc seconds. On the JCMT, there's also an FTS with SCUBA as a detector. And of course, on our shell Spire, there has been an FTS as well. But before that, the instrument that actually measured the cosmic microwave background spectral distribution was also based on the Michelson interferometer. And they won the Nobel Prize with that, so maybe I have a chance, no. But it's something that has been around for a long time, except that what we have done compared to what has been done before is that we have pushed the technology to the visible part, and also with a wide field of view, which before that was only on small fields of view. And actually, our partner ABB Bomem are specialists in FTS, and they have equipped a lot of weather forecast satellites with FTS. So the FTS technology per se is quite frequent in many places. But as I mentioned, we have pushed it to the visible part because technologically it has been very difficult to do that, and also with a wide field of view. And I was very impressed, actually at the end of the last century, there was a meeting in Hyannis in the United States about the future of what was then called the NGST. It's now called the James Webb Space Telescope. And lots of people from Europe, also from the United States and from Canada, proposed to install an imaging FTS on board the James Webb. And one paper by Charles Bennett mentioned the fact that for the purpose of seeing the earliest galaxies or the faintest possible emission line sources, the imaging FTS emerges superior to all others by orders of magnitude in speed. And so I was very impressed by that, and I said, why not try that at our own observatory, which is a 1.6 meter telescope, and try to develop this technology. So how does it work? So just very schematically, imagine that you have a monochromatic source, like a laser. Then you have the Michelson, so there's a beam splitter. The light is separated into two parts. One goes to a fixed mirror, which does not move, and the other one to the other mirror, which does move. And so you have one optical path on this side, one optical path on the other side. And there is, of course, an interference after the light comes back to the beam splitter, and you detect the interference pattern on the detector. So if the optical path from the path number one is exactly the same as the second part, then you have no phase shift between the two beams, and the interference will be constructive. But then you move this mirror slightly, the optical paths are not different, and the two beams will interfere, but not constructively. And what you will detect on the detector is a lower light level. And you do that again, you move it, and now the two are totally in antiphase, and then you get nothing on the detector. So the light goes back to the source, and for us it's not good. We don't want the light to go back to M51 or whatever, so we have to change things a bit. But essentially, schematically, it's the main principle behind the imaging FTS. So you record the pattern on the detector. It's called an interferogram. You take the Fourier transform, and you get back the spectrum from the original source. And this was for a monochromatic laser beam, but if you have any kind of spectral content here, you take the Fourier transform and you get back the spectrum from the source itself. So this is an example of what you get. On the left, you will see the interferogram being built as we move the mirror. So we take an image, we move the mirror, we take another image, and what you see here is the signal on 1 pixel. And when you take the Fourier transform, this is what you will get on the right-hand side. Oops. Okay, I'll try to stop it. Okay, so I will let it go. But at the beginning, it looks like noise, but then you take the Fourier transform and you already see something going on. And as you move along, as you move the mirror, then the spectral resolution increases. So the more you move from what we call the zero path difference, the higher the spectral resolution you get. And of course, you increase the signal to noise, but at the same time, you also increase the spectral resolution and going through the Fourier transform. This is for 1 pixel. And you imagine that instead of having just a single pixel detector, if you have a CCD, then you will have exactly the same thing for all pixels in your image. So again, this is something we've done in the lab. This is the interferogram of 2 sources. You take the Fourier transform, you get back the signal from the LED and from the helium neon laser. So as I mentioned before, I don't want half of the light to go back to the source. So instead of having a standard Michelson, we enter with some angle in order to be able to separate the first output from the input. And so you have the output, a second output here. And this is why we have 2 CCDs in the system. So an imaging FTS is a Michelson, optics, and CCDs, essentially. So it's a bit different from a standard one. So now let's go back to what we had before, but instead of having a monopixel detector, we have a CCD. This is a field on galactic supernova remnant, the Cygnus loop. I don't know if you can see the contrast, but you see some fringes here. This is for 1 detector, and you can imagine that for the second detector, you have the opposite. When you have constructive fringe here, you have a destructive fringe on the other side. So you move the mirror, you see the fringes move again, and then you can co-add all of the interferograms like that. You have a deep image. And then with the Fourier transform, you extract the spectra, and then you can color code. For example, here the red is H alpha and the blue is nitrogen 2. And you take 1 pixel here, and then you have, for example, this is the night sky, the OH lines here. And for another pixel here, you have the spectrum from the supernova remnant itself. This is a rather technical, well, the reason why it was so difficult to get into the visible band for an imaging FTS is that you have to have very good surface quality, but if you pay the price, then it's easy to get a very flat mirror with quality of about lambda over 30. You have to have very precise and stable mirror alignment, and this is really the center, the core of the technology that we have developed to be able to have a very stable mirror alignment and to maintain the relative distance between the mirrors at the same time as you take the images for a few seconds to a few minutes to better than 10 nanometers. So in the lab, it's okay, it's easy, but when you go to the telescope, it's more difficult. But we've done it, and the key to that is to have a very good servo system. So you have a laser beam going through more or less the same optical path as the science beam, and then you monitor 10,000 times per second the distance between the 2 mirrors and their orientation. And with a piezo system, you make sure that both mirrors are perfectly aligned with each other. And the key to the success of the instrument on the 3.6 meter telescope is the fact that we have built a prototype for our own 1.6 meter university-based telescope. And this has taken a long time, lots of thesis, but now these students who have done their thesis at the university, they are the main engineers for ABB now. So it was also another part of the success. And the fact that we have access to a relatively nearby telescope with lots of nights, we're able to develop the technology and the software as well. And I will come back to the software later. So the telescope, it's a 1.6 meter telescope, f8. This is Espion, which is the prototype for CITEL. The field of view was very similar, and we had 2 CCDs as well. This is the beginning of the work with CITEL at ABB. Julie here is the main engineer for the project. And this is commissioning, which was almost a year ago, a bit more than a year ago, with some students. Laurie, I think that some of you might know her because she came here. Laurie Thomas was my student. He's now my PhD. He's a really bright guy. He designed the code to reduce and analyze the data a student also from Laval, and Marc Barry, an engineer at CFHT. So again, to be technical, CITEL must be considered as an imager and then as a spectrograph, but first as an imager. And of course, by adding all of the interferogram images, then you have a very deep image. This is an example of the core of M51. It's only probably 20% of the whole field of view. So we have detectors, 2K by 2K E2V CCDs, very sensitive, up to 350 nanometers. Readout noise 4 electrons, readout time about 4 seconds. Efficiency is very good, very close to 90%, very low fringing in the red, that's very important, and it's very good still at 350 nanometers. So the whole throughput for the instrument is very high because the optics are relatively simple. So this is a total throughput for the instrument around 60% or more, and it goes down, but still at 350, it's still around 30% if you consider everything from the instrument. So again, it's an imager, so this is more or less the field of view for the Perseus cluster, and this is a part of an image, and the pixels are 0.32 arc seconds. We use filters. The filters cover most of the visible band. Now we can go, of course, closer to the near infrared. We haven't done it so far, but it's possible to do it. I don't know if the contrast is good enough, but this is an example of another supernova remnant, IC433. You see here destructive interference, and at the same time, the same field as a constructive interference on the other camera, and it's the opposite around here. So if you co-add the two images, you get 100% of the light. None of the light goes back to the source in this case. Perhaps the contrast is better on these images here. So this is, you take an image, you move it, you take an image, you move it. For a few pixels here, this is the interferogram that you have on one camera. This is the interferogram you have on the second camera. They don't look like each other, but I will flip this, and I will move it, and you can superimpose them, and they are the same. So the two images are really the opposite of each other. So you need a very, very powerful code to actually analyze the data. Something like 40,000 lines of code. I don't really understand what it means because I'm not a programmer. So Thomas Martin is really a bright guy, and he devised that. And it's kind of complicated it's not just to take the Fourier transform. You have lots of steps between an interferogram cube and a cube in the spectral domain. I won't go through that, but if you wish to talk about it, I can later. Now, CITEL as a spectrograph. Of course, the whole purpose of CITEL is to get a spectrum for each pixel. But your ILS is kind of very strange, but it's very typical of an FTS. It's a sync function, right? So this is a part of the planetary nebula. You have the nitrogen 3, nitrogen 2, H alpha, nitrogen 2, the two sulfur lines. And what you see here are not artifacts, they are part of the line itself. So if you do not have the proper code to actually fit all of the side lobes, then it's very difficult to extract all the information. But the fact that you can find information on the nitrogen line up to here, it really helps in defining the line itself and getting a very good precision, for example, on the line center and then the velocity of the gas. So this is an expanded version of the ILS. And the full-width half-max, the spectral resolution, depends on the optical path difference, as I mentioned before. So when you go through a cube, it can look very strange. This is an example of a M167, a nebula around a Wolf-Rayet star. So let's go through the H alpha. Here you have two images with positive data, positive signal, and then two images on both sides with negative signal, but it's still part of the signal, so you can extract the negative part of the signal and take it as, to get the entire flux of the nebula. And ARCS is the fitting program that actually does that and fit everything and get you the flux and the central position of the line. This is an example of the 2 nitrogen lines on nebula around the nova. There is no hydrogen here, but you can see the data in blue, and the red is the fitting, the fit that was provided by the code. So the first target that we had was N57, a very bright object, of course. But what we wanted to do with that is to make sure that the sync function actually was the exact sync function that we wanted from the instrument, and that there was no problem with the instrumental line spread function itself. And of course, it's almost textbook. Just to get you an idea of the number of steps you need to get a good spectral resolution, this is an example of NGC 628, spiral galaxy. With this filter, which is for which the aim is to get the nitrogen, H-alpha, and sulfur 2 lines. To get a resolution 1500 requires 275 mirror steps, 30 seconds per step, plus the overheads, 2.5 hours to get essentially the faint H2 regions at the periphery of the galaxy. So this is the theoretical spectral resolution we can get with the instrument. So the instrument itself can reach up to even 30,000. We haven't tested that. On the sky, we have tested up to 5,000, and it works very well. And using a different filter or using observing a relatively bright object, we could push it to about 10,000 without any problem. Wavelength calibration is relatively easy, especially in this filter. We use the OH line to calibrate with relatively good precision. Now the big question. Lots of people ask me about absorption line. Can you do absorption? Because Fabry-Perot cannot do absorption, so can an FTS do absorption? Well, 99.999% of all FTS around the world do absorption. But of course, they do absorption with a lot of signal. And this is why in CITEL, it's an imaging spectrograph to do emission lines. And that was the purpose of the instrument, to study emission lines. But the question is, can we do absorption? The reason why absorption is relatively difficult is that, contrary to a Fabry-Perot, what you get with an FTS, at each step, you get the entire bandpass, right? So with the entire bandpass, you get the photon noise from the entire bandpass as well. So you have advantages. You have deep images, all the lines get in at the same time, and Fourier does the sorting. So it's very good for emission lines with relatively low background. But the disadvantage is that you have the photon noise from the entire bandpass. So if you want to observe a continuum source with absorption lines, then you get the photon noise from the continuum as well. So it's the reason why it's more difficult. So it's clearly not ideal for absorption lines, but we can do some absorptions. And these are some examples. In ARP 94, and I will come back to that if I have time. This is for one of the galaxies in the interacting system. You see the calcium HNK here, and other absorption features. This is in the star-forming region in the galaxy, in the Milky Way. You have the lithium absorption feature here. And here, this is a cluster at a redshift of 0.28, and for some galaxies you can get, the contrast is horrible. You probably don't see that, but the calcium H and K lines are here. So it's not ideal to do absorption, but it's feasible. So if you want a niche for CITEL, you have to have an extended target because of the wide field of view, large filling factor, and emission lines, then that's perfect for CITEL. It was based on that principle. This is what we wanted to have. So some science. First paper just was accepted just a few weeks ago. It's a paper that describes the famous ILS and the equations that we use to fit everything. But the second part is about M57. And it's quite strange, and it kind of struck me that an object that is visible with a pair of binoculars, there is still something to learn about these very bright objects. And this is what we've done. We've obtained the velocity in H alpha and in nitrogen 2. This is some examples of the velocities that we get for the knots in the outer part with the error in kilometers per second, 0.7 kilometers per second or so. And in the core, the error is very close to 100 meters per second in terms of precision in the radial velocity. This is simply a Doppler image of the nebula. The second paper was, which has been accepted just a few days ago, was a study of the nebula around the nova, ATC and C. And so we've observed the knots around it by using the nitrogen 2 lines. We've measured the velocity, and then we've obtained a 3D view of the nebula. This is the first data cube that actually pushed the resolution to 5,000, a project by Gregory Erchek in China. It's a star-forming region in the Milky Way, so when you take an image, a deep image, you are completely dominated by the scattered light. But then when you take a spectrum, you can extract the H alpha, and it looks like this. So these are examples of some spectra around. This is a Herbig-Arrow object, very strong sulfur 2. This is the diffuse gas around it, the H2 region itself. And what you see here are actually emission line stars and some spectra of these emission line stars. Here you see the H alpha, which is clearly bipolar lithium 6707 absorption here as well. Orion is also very bright. You can see it with binoculars, but we wanted to push the resolution in the blue. And this is a map of the electron density based on the doublet, the oxygen 2 doublet at 37, 26, 29. Usually we use the sulfur doublet in the red part, but then you can do the same with the oxygen 2 doublet in the blue. Can I just close it to have the best contrast possible? I don't know if it will be feasible, but it's a cube we have obtained relatively recently. No, it was the light. Yeah. Thank you. I think it's okay. So it's a cube of the center of M31, and as I mentioned before, getting spectra on a very bright continuum background is relatively difficult with an FTF, and we wanted to see how faint we could go. And we'll go through the nitrogen 2 line. So we are going through the cube here. And then you will see the H alpha. At some point with the H alpha, of course you have the diffuse, but then you will see some planetary nebula pop up here and there. And I spent one evening looking at, looking for point sources in H alpha, and I find 400 in this part. Probably all of them are known. I don't know. I haven't gone through it, but the main purpose was to get this faint gas. So we have a Doppler map of the gas at the center. We have spectra of planetary nebula, supernova remnants, diffused ionized gas, and the stars, and you see absorption features here. And this is interesting. You see the sulfur 2 doublet. The two lines here are from the Milky Way, and the other two are from the M31. These are in wave numbers, so the blue is here and the red is here. We wanted to test also if Citel was okay during the full moon, again, to test how faint we could go with a very bright background. And so this is M51, H alpha plus continuum. This is the Doppler map. The core of M51 with the C at CFHT is relatively good, 0.7 arc seconds on average, and what you see here are planetary nebula. This is the AGN with very strange peculiar kinematics. This is the companion. The contrast is not very good, but you see gas around here. This is in the center, so you see the absorption in H alpha, the 2 nitrogen 2. And here you see the absorption in calcium and iron. And Of course, this is the deep image, so you can co-add all of the images. You can have a deep image, and this is a galaxy in the background in the continuum and in H alpha here at the redshift of 0.016. We wanted, of course, to show that it was possible to go to the blue part, and this is NGC 3344 at 370 nanometers, the continuum. And this is the oxygen 23727 emission line. NGC 628, a paper by Laurie, a single cube to cover most of the galaxy. BPT diagram here, luminosity function of the H2 regions. In this way, in the project that Laurie is doing, we have been, of course, a lot inspired by Khalifa, and this is why Laurie came and Carmel also came here to work with people working on Khalifa data. This is ARP94, and the purpose was to show that it was possible to get absorption. But in the core, you have emission, different profiles for different regions around the core. Again, absorption features in the elliptical galaxy here, but also you see emission in the core. And the deep image. And also what is kind of fun is that the field is so wide that you have serendipitous discoveries of galaxies in the background. So this is an example of a galaxy. This is the O2 3727 redshifted. This is the emission line here, a shift of 0.126, and we have a rotation curve based on the O2. Another galaxy more or less at the same redshift here, another one here, and another one here which is at redshift of 0.25. Stefan's quintet, it's a work that Jorge and I are doing, and this is why I've been here for the past few days to work with him on that. This is the deep image, and these are some spectra of H2 regions in the tidal tails. NGC 7320 in H alpha, this is the foreground galaxy that is not related physically to the cluster, and absorption features in one of the galaxies. And it's a combination of the light at 370 and 500 nanometers. Then we've tried to push it to clusters, and what you see here, someone probably didn't clean part of the optics or the filters or whatever, so you clearly see that in the deep image, but not in the spectra themselves. So a comparison between HST, ACS, and CTEL. So of course, the image quality is not as good as HST, but still, it's not bad. We go deeper because the exposure time was quite long. But then this is an example of a spectrum from the galaxy. This is the oxygen 2 3727 emission line, and this is a spectrum from this part. Oxygen 2, the 400 nanometers break, and the H delta absorption. And then here and there you find lots of things, and the purpose of this observation was to determine the star formation rate in this cluster in particular. Beautiful galaxy, specially resolved oxygen 2. Another galaxy in the same cluster at the same redshift with calcium H and K in the break here. Lyman alpha does not belong. Lyman alpha galaxy does not belong to the cluster. Redshift of 2.6. And again, this was another relatively mid-redshift cluster, the HEDEX pilot field, and just to show that we can observe absorption lines in this cluster, G of 20 or so. So CTEL pros and cons. There are, of course, lots of advantages, lots of disadvantages. The clear advantage of this is that you can reach a relatively wide field of view. My aim was initially to go to 20 arc minutes with the CFHT, but it was just too big. For the optical design, it posed some problems, and it would have costed more as well. You don't need image reconstruction because you take actually images. The throughput is very high. It's optimized for emission lines, so I would qualify it as an ionized gas machine. You have to compromise between spectral coverage and resolution. You have to use filters if you want to go to high spectral resolution. Otherwise, you can cover the entire visible band, but with a relatively low spectral resolution. And it's not optimized for absorption, although it's, as I've shown, it's possible to do absorption. Now, possible improvements on what we have done. To reduce the overhead, the 3.8 seconds include both the read time. Actually, it's completely dominated by the read time of the CCD. It's 3.8 seconds. And at the same time as we read the CCD, we move the mirror. To move the mirror and to stabilize the interferometer takes about 1.2 seconds. So it's completely dominated by that. But on both sides, it's possible to reduce this time to less than half a second. We could reduce the CCD readout noise. We're not dominated by CCD readout noise, but it's still possible to reduce it to less than 1 electron. To have an on-axis design, when we started the project in 2009, we wanted to have an kind of an on-axis design, and instead of having a mirror and to have a very accurate system to control the position of the mirror, we could have used a corner cube system. But to go to the UV part, we asked to many companies if they were able to quote us something to the requirements that we wanted. And at that time, it was very difficult. It would have been very, very costly. But now, 8 or 9 years later, maybe it's possible. And it would also help. And eventually to think of having multiple arms, to separate the blue and the red, and to have 2 Michelsons to do the red and the blue at the same time, that would be a good idea as well. So thank you very much.
Thank you.
What was the estimated cost of the project, and what is the sensitivity of this instrument at the frequencies?
Okay, the cost of the instrument, there are many answers to that. I received a grant of about $2.3 million, so maybe 1.8 million euros. ABB put a lot of money in that because they see that as a good window for their technology. Pushing to the visible, to the near UV and wide field of view, it was something for them. So I think they put something like, well, they didn't give me numbers, but it's around $500,000. But if you want to do it from the start and add up everything, probably around $4 million for this instrument, more or less. I don't have access to the numbers that they have, and but it's a ballpark number. And in terms of sensitivity, it depends on the wavelength range, it depends on the resolution you have, but the most commonly used filter is the SN3 around H alpha. And for example, for an H2 region, it's very close to 10 to the minus 17 ergs per second per square centimeter. That we reach. If you co-add, for example, in the M31 data cube that we have seen, if you co-add many pixels to get the diffuse interstellar gas, then we've been to a few times 10 to the minus 18 as well in the SN3 band for about a 4-hour data cube.
Yeah, it was a similar question related to the typical exposure chart that you have for extragalactic targets and galactic targets.
For galactic nebula, typically 1.5 hours. For extragalactic, we've pushed it to 4 hours. It's possible to actually go beyond that. And one thing is that you can start a cube on one day and continue it the next day. It's possible now. It was not possible with the prototype, and it was a big problem for us. We started the cube, and then clouds would come, and it was over. We lost the cube. But at CFH, it's possible to do it on multiple nights. So typically, for extragalactic targets, for galaxies, for example, for NGC 6 to 8, I would say 2.5 hours for each of the filters. So if you want to get The oxygen 2, H beta O3, and H alpha nitrogen 2, it's 3 times 2.5 hours. For the clusters, the galaxy clusters, we pushed it to 3.5 hours.
First of all, congratulations, it's fantastic.
Thank you.
And I was really struck and mentally comparing to the work that I'm doing with IQ. Now, I was also struck with the extremely high efficiency that you obtain. Keeping in mind now the comparison that you have, or the trade-off that you make, and the disadvantage you quoted, for example, for absorption lines. If you wanted to look specifically on a survey of a nearby galaxy, and here in Colorado we could think of local group, of course, which is not accessible to news. If you make a fair comparison, you have this huge field of view as opposed to the largest eye view that exists, which is news, 1 arc-minute square. Go to the same telescope, etc. Would you be able to make this exercise and tell you where the break-even point is? Also keeping in mind that the disadvantage that you quote, that you have to trade coverage with resolution, which you also could take an advantage, because most of the time you don't really need high resolution for the entire spectrum. Yeah. Would you have an answer for a comparison IFU versus FTS?
Well, and I discussed that with Roland Bacon a few weeks ago. If I could have a muse with an 11 by 11 arc-minute field of view, I will go for that, without any question. If you want an FTS, the big advantage is really the wide field of view. And also you can push the resolution. Muse goes up to 3000 or something like this. We could push CITEL further than that. But if personally had the choice between a gigantic IFU 11 by 11 arc minutes Muse type, I would go for it because you can do absorption at the same time as emission. If you're interested in emission sources only, then this is really, really good. This is the best instrument you can imagine for emission lines on wide field. But as you've shown before, the things that you do, we cannot do it with CITEL. That's very clear.
One more question? Yes.
I think that you show us that you are using a CCD 231-84 E2B. I don't understand how you can get a signal to noise ratio of, a readout noise of 4 electrons, or even 1 electron in the feature with such a short readout time.
I'm not an expert in CCDs, but first we have 4 quadrants, so yes. 4 electronics.
Okay.
So that this helps. So we read essentially 1000 by 1000. It's 2K by 2K, but we read 4 times 1K by 1K. So it helps.
Yes.
All right. Then if there is no more question, we thank very much, Roland. And we continue the discussion on IFTS with Jorge Iglesias Paramount.
Con tranquilidad. Es mucho mejor. Vale, ahora conectamos el USB.
So thanks, Laurent, for this nice introduction to EFTS. So you did most of my job now. So what I want now is just to make you think about how your science could benefit from having an IFTS in Calar Alto. So I will show from my side the science we do in my group, And then I will show which would be the niche for an IFTS at Calar Alto with the current instrumentation we have. So, well, some short introduction. As you showed before, an IFTS is basically a Michelson, where you do interferograms moving just one of the mirrors. So you take all the frequencies at each step, and then what you get is a cube, but not the classical cube where the third dimension is the wavelength, but the difference of optical path. After an appropriate data reduction, Fourier transform, and so you get our classical cubes. And this means that as for each pixel of your CCD, you have the whole spectrum. This means that you can have images of all the emission lines you have scanned within the transmittance window of your filters, even if they are quite close from each other. If your spectral resolution allows it, you can have separated all the emission lines. This is important. So IFTS in optical are now a reality, as Roland showed. First one is SPIOM in a 1.6 meter telescopes, and here you see the field of view of SPIOM is the red square compared to the size of the moon, so it's quite nice for a 1.5 meter telescope, and also CITEL for a 3.6 meter telescope, which is very similar to the 3.5 in Calar Alto. You see the transmittance of CITEL, which is good even for wavelengths lower than 4000, which is good for people working nearby galaxies for having the oxygen 2 lines. And what happens with the science of that we can do with an IFTS? Well, I will show you a little bit of how the science we do in our group at the IAA would benefit from that. And first thing is basically it's clusters of galaxies. We have been working for years in star formation rates in clusters of galaxies. And for this, what we did was wide field imaging with narrowband filters. A narrowband filter including the H-alpha line plus a continuum filter. Problems with this that, well, first, you include also the nitrogen 2 lines because your narrow filter is never as narrow as to isolate completely the H-alpha line. So you have to deal with the nitrogen contamination. Another point is that in a cluster, the radial velocity distribution is very large. So sometimes some of the cluster galaxies with the largest recession velocities or which are those which are approaching more to us, the H-alpha line will be out of the transmittance window of the cluster, and this is another problem. These are limitations of this system. But anyway, you are able to produce H-alpha images with nitrogen 2. We did H-alpha luminosity functions and so, but we had to correct in many cases statistically for these limitations. Then with this data, you produce the typical cluster-centric trends of the star formation rate with the density of or with the radial distance to the center of the cluster, just to see which of the physical mechanisms acting in clusters are more important, suppressing the star formation rate of the galaxies, like tidal stripping, starvation, and so. But I say this technique has limitations. Another very important thing that you do with the H-alpha images is study the 2D distribution of the H-alpha emission in individual galaxies. Because by studying this, the morphology of the H-alpha emission, you can also have an idea, as I said before, on whether it's tidal stripping or starvation or just collisions between galaxies, where it's deforming or just acting on this morphology. But this, for the galaxies we see in the cluster, this is easy because you see the galaxies. But sometimes there is gas outside of the galaxies, ionized gas, and it's not easy to see, first because it's not associated to galaxies. So you find it by chance, serendipitously. So I put here an example in this is the cluster Abel 1367, and we found in very deep H-alpha images tails of ionized gas. They are at the very limit of the detection, but they are real. But you find them by chance. If you focus just on individual galaxies, you will never see this. And they are related to physical processes acting on clusters, as I said before. Another example, this is from Subaru. You know, in the coma cluster, the H-alpha filaments, which are in red, are outside of the galaxies. So this is very important to have an instrument that provides a complete spatial coverage of your cluster or the set of objects you want to study, if you want to have access of this kind of filaments, which are very interesting themselves. Another important point, we found also by chance in our H-alpha images very, very compact and very active in star-forming galaxies. As you see here, this is the image containing the narrow filter. This is the continuum one. But you see, it's almost point-like. So in regular surveys, it can be mistaken like a point-like source, like a star. But these are galaxies. And if in imaging surveys they are taken as stars, you will never get a spectrum of them. So we got a spectrum because we found by chance in our images, and you see that these are galaxies. So if you don't want to lose these small galaxies that maybe are ubiquitous in cluster or not, we still don't know. You need a very wide field instrument with the possibility of scanning at all wavelengths, at least in the wavelength range of your interest. So, in this aspect, we would benefit a lot of having an IFTS for this kind of science. More things we have done, gas abundances in cluster galaxies. Here is the result of a study by Petropoulou and collaborators in 2011. And here what you see, the blue dots are dwarf galaxies, and this strip of magenta, green and red stars are spiral galaxies. And this is a plot of the local density and metallicity, and as you see, for the spiral galaxies, even part of them or integrated one, you see almost our horizontal branch. I mean, there's no relation to the local density, but the dwarf galaxies are affected by the local density. They are more enriched. The larger the local density where the dwarf galaxy lives, the more enriched it is in metallicity. And also, you see for the same galaxies, the diagram, stellar mass, metallicity, and you see this is the sequence, and we see that these galaxies, which are part of these dwarfs, but those which live in the densest environments, are overabundant in metals with respect for galaxies in less dense densities with the same stellar mass. So again, this kind of studies would benefit a lot of having IFTS, because we could have the whole spectrum for all galaxies in the field. More things we have done in our groups, to study the properties of ionized gas in early type galaxies. The example I put here by Carolina and collaborators was done with PPAC at Caja. It works with two elliptical galaxies which are not in clusters, but you can extend this kind of studies, study how is the H-alpha emission, the O3 over H-beta emission, because to cluster of galaxies, near the center of cluster of galaxies, there are lots of ellipticals, so you can study, you can extend this kind of studies to clusters, and again, with an IFTS, with the appropriate instrument. Now we go out from clusters, we go out to blue compact dwarf galaxies. Recently, Carolina published a paper where she found in OneWiki 18 an extended H2 emitting regions. This is the contours are H-alpha emission of the galaxy. This is PIMA, and this is the size of the H2 emitting region. And well, this is an example for a local galaxy, but we know that there are samples of galaxies of large surveys with narrow H2 emitters in ultraviolet, but redshifted to the optical. are potential candidates for hosting what we call populating 3 star, or kind of populating 3 star. I mean, stars that would be would have a very low metal content, and that would be the origin of these helium-2 emitting regions. So for this, again, imagine you have a cosmological field, you have a wide field IFTS, and you scan a range where the wavelength of your interest would be, and just blindly you will find a lot of these emitters, and then once they are localized, you just change your filter and you study the whole spectrum. So this would be, again, ideal for an IFTS. So, well, you can think of your favorite science project, and you can think how having an IFTS would benefit from this. So, what if we build an IFTS for Calar Alto? This is the list of wishes. It's basically CITEL works, so we can do something like CITEL with respect to the field of view. I would try to go as wide as possible. I would say between 10 and 20. 10 it works, it's okay, but can we go between 15? I don't know. We can say between 10 and 20. Spectral coverage from 3,700 to the micron, basically, a little bit less, but which is basically the optical where most of the emission lines of our interest are. Resolving power, you have from 1 up to 20,000 without problems, and I think it would be important if we can adapt it also for the 2.2 meters. It would be less sensitive, but it would be good to put either in the 3.5 or, if possible, in the 2.2. For this, I think we should build an adapter or something like this, but I think it will be possible. And this is the current instrumentation in Calar Alto for the 3.5 meters, for the 2.2, and let's see a comparison of, for example, this is the wavelength where the spectrographs work, the spectral resolution. You have CAFOS, PIMAs. Well, Café and Cármenes are below the plot, but they are there. So, an IFTS with the characteristics I showed before would cover all this area. It would be okay. Maybe we could push a little bit higher in spectral resolution, but up to 20,000 could be okay, or even a little bit less. But it would cover, at the same time, CAFOS and PIMAs, basically. Fields of view. These are basically imagers. I put here also the PIMAs with the lens array and PPAC. Be careful because all this is at the same scale, but here is 4 times enlarged, so that you can compare. Otherwise, it was too small. You have PANIC has a very big field of view, especially adapted to the 2.2 meters. So the IFTS, if we have between 10 and 20, would be something like this. So not the biggest one, but comparable in size. And remember that it's not just an imager; it does also spectra, because most of the biggest one are doing just imaging. Multiplexing. You have CAFOS is basically long slit. PIMAS has a nice multiplexing, 2056 in the lens array configuration, and 331 fibers in the PPAC configuration. Café and Cármenes are very high resolution but single aperture, and an IFTS would be something like 2K by 2K. Imagine just typical detector is about 4 million. So, in my opinion, the niche for an IFTS at Calar Alto would be the wide field of view, as wide as possible, of course. The fact that you can switch from intermediate to high spectral resolution and it's variable, you decide just before serving, and a very high multiplexing. And that's all. Thank you. So, well, just one thing. This presentation is just to motivate you to find your favorite science case. Maybe we can discuss later during the coffee break, because if we want to someday have an instrument like this, we should put ideas in common and everything, but it's time to start thinking about that. Sorry.
test run of CTEL worked at a 1.6 meter, but if you take CTEL, would that live at a classic run focus at the 2.2 weight related?
I think it should be like this, yeah. But at the moment, this is just an idea. We should see design, and so I think it should be very similar because the telescopes are not so different.
One of the really big advantages, if you have a configuration which works on those, that you have wide field or really wide field with the same instrument as a somewhat smaller telescope. So you have a survey instrument and the detailed studies for the two telescopes.
Yeah.
Nice distributed.
Yes.
It was a very related question about being located in the Cassegrain focus and maybe on axis to see, well, Logan proposed before. It will be in the Cassegrain, right?
But this is the idea, yes. But I say, still, there's no design, or it's just, at the moment, it's just idea. In principle, yes.
Jesus?
Do you know what is the key element that defines the field of view? I mean, it's just only a matter of the optics in general, or is because of the filter size?
No, well, I'm not an expert. Maybe Laurent can answer yes, but it's not only optics, for sure, because the angle of incidence, I think, no, for the field of view, you mean, is limited in partly by the angle of the off-axis configuration, maybe, I think.
In part, but also the size of the lens.
Yeah.
Yes. The focal
So-
ratio, because if not, it will be too large or you have to put a lot of mirrors.
But with the plate scale of the 3.5, the size of the optical lenses would be, for 20 arc minutes, about 20 centimeters. About 20 centimeters.
That would be a factor of 2 at the 2.2, which is faster F ratio and the smaller focal lenses, right?
Mhm.
More questions? All right then. Thank you very much, Jorge.